Millions of years ago, Earth had a very different arrangement of land and oceans. The continents were connected into one large landmass called Pangea, which existed during the late Paleozoic and early Mesozoic eras. This enormous continent contained diverse environments, including mountains, forests, deserts, and coastal regions where many ancient organisms lived. Pangea formed through the movement of Earth's tectonic plates and later separated as these plates continued to shift. The breakup of Pangea created the continents that exist today and influenced global climate patterns, ocean circulation, and the development of life. Before the giant landmass known as Pangea came into existence, the Earth had already passed through an extremely long period of change. The planet did not begin with continents, oceans, forests, rivers, or mountains that looked like those seen today. During its earliest history, Earth was a very different place. It was a young planet that was still forming after the birth of the solar system. Understanding this early period helps explain how the first continents appeared and why they eventually joined together to form larger landmasses, including Pangea. Every continent that exists today has its roots in events that took place during this distant period of Earth's history. Earth formed about 4,540,000,000 years ago from a huge cloud of gas and dust that surrounded the young sun. Tiny grains of dust began sticking together because of gravity. As they became larger, they collided with other pieces of rock and metal. These repeated collisions slowly built larger bodies called planetesimals. Many of these early bodies crashed into one another. Over time, one of them grew into the planet that would become Earth. The process took millions of years and involved countless impacts that released enormous amounts of heat. The young Earth was not a cool and peaceful world. It was extremely hot. Heat came from many sources. The constant impacts of large rocks released energy. The pressure inside the growing planet also created heat. Radioactive elements within the Earth produced additional heat as they broke down naturally. Because of this intense heat, much of the young planet melted. Instead of having a solid surface, Earth was covered by vast areas of molten rock. This stage is often called the magma ocean because much of the outer part of the planet existed as flowing liquid rock. As the planet remained hot, heavy materials such as iron and nickel slowly moved towards the center. Lighter materials stayed closer to the surface. This process separated Earth into different layers. The center became the core, which is mostly made of iron and nickel. Around the core formed the mantle, made mainly of hot rock that can slowly flow over long periods. Above the mantle developed the crust, which became the thin outer layer of solid rock. This layered structure remains part of Earth today. The earliest crust was very different from the continents that exist now. It was thin, unstable, and often destroyed by the heat rising from below. Large cracks opened across the surface. Fresh molten rock rose through these openings and cooled. Some areas of the crust broke apart while new crust formed elsewhere. The young surface changed again and again as heat continued escaping from deep inside the planet. During this time, Earth had no permanent continents. Small pieces of solid crust formed, broke apart, melted, and formed again. The surface was constantly changing because the inside of the planet still contained enormous amounts of heat. Much of the crust could not survive for long before being recycled back into the mantle. As a result, very little rock from this earliest period remains today. The atmosphere during Earth's earliest history also looked very different from the one that surrounds the planet today. It did not contain enough oxygen for humans or animals to breathe. Instead, it was filled with gases released by volcanoes. These gases included water vapor, carbon dioxide, nitrogen, sulfur compounds, methane, and ammonia. Volcanoes were extremely common because the planet's interior was much hotter than it is today. They released huge amounts of gas into the atmosphere over millions of years. As the planet slowly cooled, water vapor in the atmosphere began turning into liquid water. Thick clouds formed around the planet. Rain fell for very long periods. Some of the rainwater collected in low areas of the surface. Over time, these growing bodies of water became the first oceans. Scientists believe that additional water may also have arrived through impacts from icy objects such as comets and water-rich asteroids. Together, these sources helped fill the oceans that covered much of the planet. The early oceans were different from those of today. They were warmer and contained different amounts of dissolved minerals and chemicals. They were influenced by frequent volcanic activity beneath the water. Hot water carrying minerals flowed from cracks in the ocean floor. These underwater volcanic systems played an important role in shaping the chemistry of the oceans and the rocks forming beneath them. Even after oceans appeared, the Earth's surface remained active. Large amounts of heat continued moving upward from deep inside the planet. This heat caused parts of the mantle to rise while cooler material slowly sank. These movements created forces that pushed and pulled the crust above. Over very long periods, these forces became responsible for the movement of Earth's outer rocky plates. This process, known today as plate tectonics, became one of the most important systems controlling the formation of continents. Scientists continue studying exactly when modern plate tectonics began. Some evidence suggests that forms of plate movement started very early in Earth's history. Other evidence suggests that the system developed gradually over hundreds of millions of years as the planet cooled. Although researchers continue examining this question, there is strong agreement that movement of the crust eventually became a major force shaping Earth's surface. The earliest pieces of continental crust began forming when molten rock cooled and hardened into lighter types of rock. These rocks contained minerals that made them less dense than the rocks beneath the oceans. Because they were lighter, they floated higher on the mantle. This allowed them to survive longer instead of sinking back into the deeper parts of the Earth. Over time, these stable pieces grew larger as more material was added to them. Some of the oldest known minerals found on Earth are tiny crystals called zircons. These crystals formed more than 4 billion years ago. Scientists study them because they preserve valuable information about conditions on the early Earth. By examining their chemical makeup, researchers have learned that liquid water probably existed very early in Earth's history. These zircons also suggest that some form of continental crust had already begun forming during this distant period. Finding rocks from the earliest Earth is extremely difficult because geological activity has recycled much of the ancient crust. Most early rocks have been melted, buried, broken apart, or changed by heat and pressure. Only a few small areas around the world still contain rocks that formed during those ancient times. These rare rocks provide important clues about how the first continents developed. As small areas of continental crust survived, they slowly joined together. New volcanic material hardened along their edges. Collisions between pieces of crust caused them to merge into larger blocks. These growing landmasses became the foundations of future continents. The process was very slow and continued over hundreds of millions of years. The early continents did not look like modern ones. Their shapes were different, and many were much smaller. They were scattered across the surface instead of forming one giant landmass. Some existed as isolated islands surrounded by wide oceans. Others formed groups of connected land. Their coastlines changed constantly because volcanic eruptions, earthquakes, and crustal movement reshaped them over time. The climate during this early period was also changing. The young sun produced less energy than it does today, yet the Earth remained warm enough for liquid water to exist. Scientists believed that greenhouse gases in the atmosphere trapped heat and helped keep temperatures suitable for oceans. Carbon dioxide and methane played especially important roles in holding warmth close to the planet's surface. Volcanic eruptions continued releasing fresh gases into the atmosphere. Lava covered wide areas of land. Ash spread across the landscape. New mountains formed where pieces of crust collided. Other mountains slowly wore down because of wind, rain, and flowing water. The broken rock was carried into rivers and eventually reached the oceans, where layers of sediment slowly accumulated. As sediments collected over long periods, they hardened into sedimentary rocks. These rocks preserved records of changing environments. They also helped build thicker sections of continental crust. Heat and pressure deep within the Earth later changed many of these rocks into metamorphic rocks. Molten rock cooled into igneous rocks. Together, these rock types became important parts of the growing continents. The movement of Earth's crust caused repeated cycles of growth and destruction. Some pieces of continental crust collided and joined together. Others split apart because of forces pulling the crust in different directions. Ocean basins opened and later closed. Mountains rose and gradually wore away. Throughout all these changes, the amount of continental crust slowly increased. The first continents were not lifeless for their entire history. At some point during Earth's early development, simple microscopic life appeared. Scientists continue studying exactly how life began, but evidence suggests that tiny living organisms existed at least 3,500,000,000 years ago and possibly even earlier. These early forms of life lived mainly in the oceans. They were single-celled organisms with very simple structures. Many of these tiny organisms obtained energy through chemical reactions involving substances found in the water. Later, some groups developed the ability to use sunlight to produce food through photosynthesis. Early photosynthesis gradually released oxygen into the oceans and eventually into the atmosphere. At first, much of this oxygen reacted with iron dissolved in seawater. These reactions formed iron-rich rocks that can still be found today. Over very long periods, oxygen slowly accumulated in the atmosphere. This major environmental change transformed Earth's surface. It affected the chemistry of rocks, oceans, and the atmosphere itself. Many early organisms could not survive rising oxygen levels, while others adapted to the changing conditions. This shift became one of the most important events in Earth's biological history. As continents continued growing, they influenced weather patterns, ocean currents, and the movement of nutrients across the planet. Rivers carried minerals from the land into the oceans. Coastal environments developed where land met the sea. Shallow waters provided places where sediments gathered and living organisms thrived. The interiors of the growing continents contained ancient rocks that became increasingly stable. These regions are known today as cratons. Cratons form the oldest and strongest parts of modern continents. Many have survived for billions of years despite repeated geological activity around them. They acted as long-lasting foundations upon which younger rocks were later added. Different cratons slowly expanded as volcanic activity and continental collisions attached new material to their edges. Each addition increased the size of the continents. Some new rocks formed from cooled magma rising from below. Others were pieces of crust carried by moving plates rising from below. Others were pieces of crust carried by moving plates before becoming attached to larger landmasses. This gradual growth continued throughout much of Earth's history. The boundaries between moving plates remained highly active. Earthquakes occurred when rocks suddenly shifted. Volcanoes erupted where molten rock reached the surface. Deep beneath the oceans, new crust formed while older crust was pushed downward into the mantle. These ongoing movements reshaped the arrangement of oceans and continents over immense spans of time. The first continents did not remain fixed in one location. Like the continents of today, they slowly drifted across the surface because they rested on moving tectonic plates. Although the movement was very slow, covering only small distances each year, millions of years allowed enormous changes to occur. Continents gradually approached one another, separated again, and followed changing paths across the globe. Their movement eventually led to the formation of larger supercontinents that existed long before Pangea. These earlier landmasses became important stages in Earth's long geological history and prepared the way for the later assembly of Pangea. The movement of continents is one of the most important natural processes in the history of Earth. Today, the continents appear fixed in place, but they are actually moving all the time. This movement is extremely slow, so people cannot notice it during their lifetime without using very accurate scientific instruments. Over millions of years, however, these small movements become very large. Continents that were once joined together can slowly move far apart, while others that were once separated by wide oceans can gradually come together. This slow movement has changed the appearance of Earth many times throughout its long history. Scientists explain this movement through the theory of plate tectonics. Plate tectonics is the scientific idea that the outer shell of Earth is broken into many large and small pieces called tectonic plates. These plates are always moving across the surface of the planet. The continents and the ocean floors rest on these plates, so whenever a plate moves, the land and the ocean floor move with it. This movement is responsible for the changing positions of the continents, the opening and closing of oceans, the building of mountain ranges, the formation of volcanoes, and the occurrence of many earthquakes. To understand plate tectonics, it is first necessary to understand the structure of Earth. Earth is made of several layers. The outermost layer is called the crust. This is the solid surface on which people live. The crust is much thinner than the deeper layers of Earth. Beneath the crust lies the mantle, which extends to a great depth inside the planet. Below the mantle is the outer core, which is made mostly of liquid iron and nickel. At the very center is the inner core, which is solid because of the enormous pressure found deep inside Earth. The crust and the uppermost part of the mantle together form a strong outer layer called the lithosphere. The lithosphere is not one single piece. Instead, it is divided into many separate tectonic plates. Some of these plates are very large and cover huge parts of Earth's surface, while others are much smaller. Every continent and every ocean rests upon one or more of these moving plates. Below the lithosphere is a layer called the asthenosphere. Although it is made of solid rock, the rocks here are extremely hot and can slowly flow over very long periods of time. They do not behave like melted lava near the surface, but they are soft enough to allow the rigid plates above them to move. The movement of the plates takes place because they slowly slide across this softer layer. The heat inside Earth is the main source of energy that causes tectonic plates to move. Much of this heat comes from the time when Earth first formed. During Earth's early history, countless pieces of rock collided with one another to create the growing planet. These violent impacts release tremendous amounts of heat. Additional heat is produced even today through the natural breakdown of radioactive elements found deep inside Earth. These elements slowly release energy over billions of years, helping to keep Earth's interior extremely hot. The heat deep inside Earth causes material in the mantle to move slowly. Hot rock deep within the mantle becomes less dense and gradually rises upward. As it moves closer to the surface, it begins to cool. Cooler rock becomes denser and slowly sinks back toward the deeper parts of the mantle. This continuous movement creates large circulating patterns inside the mantle. These slow movements transfer heat from Earth's deep interior toward the surface. The moving mantle pushes and pulls on the tectonic plates resting above it, helping them move across Earth's surface. Scientists once believed that these circulating movements inside the mantle were the only force responsible for plate movement. Later research showed that the process is more complex. Several different forces work together to move the plates. These forces include mantle convection, ridge push, slab pull, and the movement caused by gravity, acting on sinking oceanic plates. Mantle convection is the slow circulation of hot and cool rock inside the mantle. As hot material rises and cool material sinks, it creates movement beneath the tectonic plates. Although this process happens very slowly, it operates continuously over millions of years. The moving mantle transfers energy to the plates above, helping them travel across Earth's surface. Another important force is called ridge push. Along the ocean floor are long underwater mountain ranges known as mid-ocean ridges. These ridges form where tectonic plates move away from one another. Hot molten rock rises from the mantle through cracks between the separating plates. When this molten rock reaches the cooler ocean floor, it hardens into new crust. Since the newly formed crust is hot, it stands slightly higher than the older crust farther away. Gravity causes this higher crust to slowly slide downward, pushing the rest of the plate away from the ridge. Slab pull is considered one of the strongest forces moving tectonic plates. Oceanic crust becomes cooler, thicker, and denser as it grows older. Eventually, when it reaches certain parts of Earth where plates meet, the heavy oceanic plate begins to sink back into the mantle beneath another plate. As this dense plate sinks, it pulls the rest of the plate behind it. This pulling force helps move large sections of Earth's surface over very long distances. Gravity also plays an important role in plate movement. Dense oceanic plates naturally sink into the mantle because they are heavier than the surrounding material. This sinking movement creates additional forces that help keep the plates moving. Gravity works together with mantle movement, ridge push, and slab pull to produce the continuous motion observed across Earth's surface. There are several major tectonic plates covering Earth. These include the Pacific Plate, the North American Plate, the South American Plate, the Eurasian Plate, the African Plate, the Antarctic Plate, the Indo-Australian Plate, and many smaller plates. Each plate moves at its own speed and in its own direction. Some move toward one another, some move apart, and others slide past one another. Their movements are usually only a few centimeters each year, but these small yearly movements become enormous over millions of years. The boundaries where tectonic plates meet are among the most active places on Earth. Scientists recognize three main kinds of plate boundaries. These are divergent boundaries, convergent boundaries, and transform boundaries. Each type produces different weird geological features and different kinds of activity. At divergent boundaries, two tectonic plates move away from each other. As they separate, hot material from the mantle rises upward to fill the gap. This material cools and hardens to form new crust. Most divergent boundaries are found beneath the oceans, where they create long underwater mountain chains called mid-ocean ridges. These ridges stretch across thousands of kilometers and represent places where new ocean floor is constantly being created. As new crust forms at mid-ocean ridges, older ocean floor is slowly pushed farther away. This process is known as seafloor spreading. Seafloor spreading continually adds new material to Earth's surface, while older oceanic crust moves toward areas where it eventually sinks back into the mantle. This ongoing recycling keeps Earth's surface active throughout geological history. Divergent boundaries can also occur on land. When this happens, the crust stretches and becomes thinner. Cracks begin to form and valleys develop between the separating blocks of land. Over very long periods, these valleys may continue widening until sea water flows in and forms a new ocean. This process has happened several times during Earth's history and continues in some regions today. At convergent boundaries, tectonic plates move towards each other. Different results occur depending on the kinds of plates involved. If an oceanic plate meets another oceanic plate, one usually sinks beneath the other into the mantle. This process is called subduction. As the sinking plate descends into the hot mantle, water trapped within the rocks helps generate molten material. This molten rock rises toward the surface and can create chains of volcanic islands. When an oceanic plate meets a continental plate, the heavier oceanic plate usually sinks beneath the lighter continental plate. This creates deep ocean trenches, powerful earthquakes, and volcanic mountain ranges along the edge of the continent. The sinking plate continues descending into the mantle, where it slowly becomes part of Earth's interior once again. When two continental plates collide, neither plate sinks easily because both are relatively light compared to the mantle beneath them. Instead, the rocks become compressed, folded, and pushed upward. Over millions of years, enormous mountain ranges are formed. The rocks continue changing long after the initial collision, creating high mountains, deep valleys, and thick layers of deformed rock. Transform boundaries are different from both divergent and convergent boundaries. At these boundaries, two plates slide sideways past one another. Since the edges of the plates are rough, they often become stuck because of friction. Stress gradually builds as the plates continue trying to move. Eventually, the built-up stress becomes greater than the friction holding the plates in place. The plates suddenly slip, releasing energy as earthquakes. No new crust is created, and no old crust is destroyed at transform boundaries. Earthquakes are one of the clearest signs that tectonic plates are moving. Most earthquakes occur along plate boundaries. The sudden release of energy sends seismic waves through Earth's interior and across the surface. Some earthquakes are small and barely noticeable, while others are powerful enough to damage buildings, roads, bridges, and other structures. Volcanoes are also closely connected to plate tectonics. Many volcanoes form where one tectonic plate sinks beneath another. As water from the descending plate enters the hot mantle, it lowers the melting temperature of nearby rocks, allowing molten material to form. This molten rock rises through cracks and eventually erupts at the surface. Volcanoes can also form where plates move apart, and magma rises directly from the mantle. Ocean formation is one of the most important results of plate tectonics. Oceans are not permanent features. They open, grow larger, shrink, and eventually disappear over hundreds of millions of years. New oceans begin when continents split apart because of forces stretching the crust. As the land separates, magma rises and forms new oceanic crust. Water gradually fills the widening gap, creating a young ocean basin. As seafloor spreading continues, the new ocean becomes wider. Fresh oceanic crust forms continuously at the spreading center, pushing the continents farther apart. The ocean basin grows larger over millions of years. Many of today's oceans were formed through this process, after ancient supercontinents broke apart. Ocean basins do not continue growing forever. Eventually, subduction zones may develop around their edges. Oceanic crust begins sinking back into the mantle faster than new crust is created. As more crust disappears beneath surrounding continents, the ocean gradually becomes smaller. If this process continues long enough, the ocean may close completely as continents move back together. Continental drift refers specifically to the movement of continents across Earth's surface. The continents do not move independently through the ocean floor. Instead, they travel together, with the tectonic plates on which they rest. This understanding solved many scientific questions that earlier ideas about drifting continents could not fully explain. Evidence supporting continental movement comes from many different scientific observations. The shapes of some continental coastlines appear to fit together. Similar rock formations are found on continents now separated by oceans. Fossils of identical plants and animals have been discovered on widely separated continents, showing that these lands were once connected. Ancient climate evidence, including signs of glaciers in areas that are now warm, also supports the idea that continents have changed position over time. The ocean floor provides additional evidence for plate tectonics. Scientists discovered that rocks nearest to mid-ocean ridges are younger than rocks located farther away. This pattern shows that new crust forms at the ridges and gradually moves outward. Magnetic minerals trapped inside cooling lava preserve records of Earth's changing magnetic field. These magnetic patterns appear as matching bands on both sides of ocean ridges, providing strong evidence for seafloor spreading. Modern technology allows scientists to measure plate movement directly. Satellites and global positioning systems can detect the slow motion of tectonic plates with remarkable accuracy. Measurements show that plates continue moving every year, confirming predictions made by the theory of plate tectonics. The movement of tectonic plates also affects Earth's climate over long periods. As continents change position, ocean currents are redirected, altering the movement of warm and cold water around the planet. These changes influence rainfall, temperatures, and weather patterns over millions of years. The location of mountain ranges also affects air circulation and precipitation. Living organisms have also been influenced by continental movement. When continents separate, populations of plants and animals become isolated from one another. Over long periods, these isolated populations evolve independently, leading to the development of new species. When continents later reconnect, species that evolved separately may meet once again. Natural resources are strongly connected to plate tectonics. Many valuable mineral deposits form in areas where tectonic plates interact. Gold, copper, silver, and other metals often become concentrated through geological processes, linked to volcanic activity and mountain building. Oil and natural gas also accumulate in sedimentary basins that formed because of plate movement. The recycling of Earth's crust is another important result of plate tectonics. Oceanic crust is continuously created at divergent boundaries and destroyed at subduction zones. This recycling helps regulate Earth's internal heat and continually renews parts of the planet's surface. Continental crust also changes through mountain building, erosion, volcanic activity, and other geological processes. The movement of plates has continued throughout Earth's history. Different supercontinents have formed and broken apart many times. These repeated cycles have reshaped Earth's geography over billions of years. Continents have travelled across different climate zones, crossed the equator, approached the poles and returned again as plate movements continued. Scientists continue studying plate tectonics to better understand Earth's past and future. Advanced computer models, satellite observations, earthquake monitoring, deep-sea exploration, and laboratory experiments all contribute new information about how plates move and interact. Although much has been learned, researchers continue investigating details about the exact behavior of Earth's mantle, the forces driving plate motion, and the ways different geological processes influence one another. Plate tectonics remains active today. Every continent continues moving, every ocean floor continues changing, and Earth's interior continues transferring heat toward the surface. Mountain ranges continue rising in some regions, while erosion wears them down in others. Volcanoes continue erupting where magma reaches the surface, and earthquakes continue releasing accumulated stress along plate boundaries. Oceans continue expanding in some places while shrinking in others. These ongoing geological processes ensure that Earth's surface remains dynamic, with continents and oceans constantly changing their positions through the slow but continuous movement of tectonic plates driven by heat. From Earth's interior, mantle circulation, ridge push, slab pull, gravity, crustal recycling, and the endless interaction of the rigid plates that cover the planet. Before the formation of the supercontinent known as Pangea, Earth had already experienced a very long history of continents joining together and later breaking apart. The surface of Earth has never remained the same for long periods of time. The land has always been moving because the outer shell of the planet is divided into large pieces called tectonic plates. These plates move very slowly across the surface. Although the movement is so slow that people cannot notice it during their lifetime, it continues without stopping over millions of years. As the plates move, continents travel with them. At times they come together to form one very large landmass. After remaining connected for a long period, they begin to separate again. This process has happened many times during Earth's history, and scientists call it the supercontinent cycle. The history of these ancient supercontinents stretches back billions of years. Earth itself formed about 4,540,000,000 years ago. During its earliest history, the planet was very hot. Its surface was covered by molten rock, and large objects from space struck it again and again. These impacts released enormous amounts of heat. Over time, the surface slowly cooled. Solid rocks formed and the first crust began to develop. This early crust was not stable. It often melted, broke apart, and formed again because the inside of Earth remained extremely hot. As the planet continued to cool, thicker pieces of crust started to survive for longer periods. These pieces became the earliest continents. They were much smaller than today's continents. They did not stay in one place. The movement of tectonic plates slowly carried them across the surface of Earth. Some pieces collided and joined together, others broke away and drifted apart. This constant movement slowly changed the appearance of the planet. Scientists have learned about these ancient events by studying rocks from different parts of the world. Some rocks are more than 3 billion years old. These rocks contain valuable information about the conditions that existed when they formed. By studying their age, minerals, chemical makeup, and magnetic properties, scientists have been able to rebuild much of Earth's early history. They also examine mountain ranges, ancient volcanic rocks, and fossils found on different continents. These discoveries help them understand where the continents were located long ago. One important method involves studying tiny magnetic minerals inside rocks. When molten rock cools, these minerals become locked into position. They point toward its Earth's magnetic field at the time the rock hardened. Even after hundreds of millions or billions of years, these magnetic directions remain preserved inside the rock. By measuring them, scientists can estimate where the rocks formed and how far they have moved over time. Another important source of evidence comes from rocks that have the same age and structure but are now found on continents separated by vast oceans. These matching rocks suggest that the continents were once connected. Similar mountain belts also continue from one continent to another when the continents are placed back into their earlier positions. These clues support the idea that ancient supercontinents existed long before Pangea. One of the earliest known supercontinents is called Columbia. Some scientists also use the name Nuna for this ancient landmass. Although researchers continue to study its exact shape and history, there is strong evidence that many of Earth's continents became joined together during this period. Columbia is believed to have formed around 1,800,000,000 years ago. It remained together for hundreds of millions of years before beginning to break apart. At the time Columbia formed, Earth looked very different from the planet seen today. The continents that now make up Africa, North America, South America, Europe, Asia, Australia, and Antarctica did not exist in their present forms. Instead, many smaller blocks of continental crust slowly collided with one another over an extremely long period. These collisions happened because tectonic plates pushed the continents together. When two continents met, their edges were squeezed. Thick layers of rock folded and rose upward, creating large mountain ranges. The formation of Columbia involved many separate collisions. Different continental blocks came together one after another. Every collision added another piece to the growing supercontinent. Some collisions happened along the edges of ancient oceans. As the continents moved closer together, the ocean floor between them slowly disappeared beneath one tectonic plate. Eventually, the continents themselves collided, joining into one larger landmass. The mountain-building events that happened during the formation of Columbia left important evidence behind. Even though many of these mountains have been worn down by erosion, traces of them still remain inside ancient rocks. Scientists study these mountain belts to understand when the continents came together and how they were connected. During the time Columbia existed, Earth's climate differed from that of later ages. The atmosphere contained different amounts of gases, and living things were still very simple. Large animals, plants, and forests had not yet appeared. Life existed mainly as tiny organisms living in oceans, shallow waters, and coastal environments. These microscopic forms of life slowly changed the atmosphere by producing oxygen through photosynthesis. This gradual increase in oxygen became one of the most important developments in Earth's history. The oceans surrounding Columbia also played an important part in shaping the planet. Ocean currents moved heat around the globe. Volcanic activity beneath the oceans created new crust, while older ocean floor disappeared into the mantle at deep ocean trenches. This recycling of ocean crust allowed tectonic plates to continue moving over long periods. Columbia did not remain unchanged throughout its existence. The tectonic forces beneath the surface continued to act on the supercontinent. Deep inside Earth, heat moved through the mantle in slow currents. These movements pushed and pulled the tectonic plates above. Over time, stress built up inside the crust. Cracks began to develop in different regions. Some of these cracks eventually widened into long rift valleys. As rifting continued, molten rock rose from deep below the surface. Magma filled the cracks and hardened into new rock. The crust became thinner, allowing the continents to begin separating. Water entered the widening gaps, forming young seas that later expanded into larger oceans. Step by step, Columbia slowly broke into smaller continental pieces. The breakup of Columbia did not happen suddenly. It took hundreds of millions of years. Different sections separated at different times. Some continental blocks moved away quickly, while others remained connected for much longer. As the pieces drifted apart, new coastlines formed, oceans expanded, and Earth's geography changed once again. Even after Columbia broke apart, the movement of tectonic plates never stopped. The separated continents continued traveling across the planet. Some moved toward each other once again, others drifted farther apart. New oceans formed while older oceans slowly disappeared. This endless movement prepared the way for another supercontinent that would eventually develop. After many millions of years, the continents that had once been part of Columbia gradually began coming together again. Their slow movement resulted in the formation of another great supercontinent known as Rodinia. Scientists believe Rodinia formed about 1 billion years ago. Like Columbia, its exact arrangement continues to be studied because the rocks have experienced many later changes. Even so, enough evidence exists to show that most of Earth's continental crust became united once again. Rodinia was one of the largest landmasses that had ever existed up to that point in Earth's history. Many of the continental blocks that later became today's continents were joined together within this enormous supercontinent. Large mountain ranges formed wherever continental collisions occurred. Thick layers of rock were folded, broken, and pushed upward during these powerful events. The center of Rodinia consisted of older continental crust that had survived from even earlier times. Around these older regions, younger continental blocks became attached during repeated collisions. The growing supercontinent contained rocks that had formed over billions of years, representing many different stages of Earth's development. Scientists reconstruct the shape of Rodinia by carefully matching ancient rocks from continents that are now separated by thousands of kilometers. Rocks of similar age, structure, and mineral composition often fit together surprisingly well. Ancient mountain belts also line up when the continents are placed into their earlier positions. Magnetic evidence preserved inside rocks provides additional support for these reconstructions. The formation of Rodinia had important effects on Earth's oceans. As continents came together, older oceans closed while new oceans formed elsewhere. Ocean currents changed direction because the arrangement of land and water changed. These changes affected the movement of heat around the planet and influenced climate patterns over very long periods. Rodinia also existed during an important time in the history of life. Simple microscopic organisms continued evolving in the oceans. Different kinds of algae spread through shallow coastal waters. Single-celled organisms became more diverse, and some groups began living together in larger colonies. These developments gradually increased the complexity of life on Earth. Scientists continue to investigate how Rodinia influenced Earth's environment. Because such a large amount of land was connected into one supercontinent, rainfall patterns, temperatures, ocean circulation, and volcanic activity were affected. Rivers carried sediments across vast distances before emptying into surrounding seas. Thick layers of sand, mud, and other materials accumulated along coastlines and ocean floors, preserving valuable records of Earth's changing conditions. The inside of Earth continued producing heat beneath Rodinia, just as it had beneath Columbia. Mantle movements slowly placed increasing stress on the supercontinent. Over many millions of years, large cracks once again appeared across different regions. These fractures marked the beginning of another long period of continental breakup that would eventually reshape the surface of the planet in entirely new ways. The forces that caused Rodinia to come together did not disappear after the supercontinent had formed. Deep beneath the surface, the mantle remained hot and active. Heat slowly moved upward from the deeper parts of Earth. This movement caused the tectonic plates above to continue shifting. Although these movements happened at speeds that were only a few centimeters each year, they continued without stopping over hundreds of millions of years. The crust slowly bent, stretched and cracked in different places. The stresses became greater as time passed, and eventually the strong continental crust began to split apart. The first signs of Rodinia breaking apart appeared as long fractures across different regions of the supercontinent. These fractures gradually widened into rift valleys. As the crust became thinner, molten rock rose from deep inside Earth. This magma cooled and hardened to form new rock along the growing cracks. Volcanic activity became common in many of these regions. Lava flowed across the land, while ash and gases entered the atmosphere. These volcanic events lasted for very long periods because the process of continental breakup was slow and continuous. As the cracks widened, seawater entered the low areas, forming narrow seas between these separating pieces of land. Over many millions of years, these narrow seas grew wider. New ocean crust formed beneath them as magma continued rising from the mantle. The young oceans slowly expanded, pushing the continents farther apart. The edges of the continents that had once been joined became separated by growing stretches of water. The breakup of Rodinia did not happen all at once. Different sections separated at different times. Some continental blocks drifted away early, while others remained connected for much longer. The movement depended on the direction and speed of the tectonic plates beneath each region. Some pieces rotated as they moved, changing their orientation while crossing Earth's surface. Others traveled long distances before meeting different continents many millions of years later. The changing arrangement of the continents affected Earth's climate in many ways. The position of continents influences the movement of air and ocean water. When large landmasses occupy different parts of the planet, they change the paths taken by winds and ocean currents. These changes affect temperatures, rainfall, and the movement of heat from one region to another. As Rodinia broke apart, these patterns slowly changed across the globe. Many scientists believe that the breakup of Rodinia may have been connected with some of the coldest periods in Earth's history. During these times, enormous sheets of ice spread across large areas of the planet. Evidence of ancient glaciers has been discovered in rocks that formed near the equator, showing that ice reached regions that are warm today. These discoveries suggest that Earth experienced very widespread freezing during parts of this period. Scientists continue studying how the changing positions of continents may have influenced these global climate events. The oceans also changed as Rodinia separated. New coastlines appeared as the continents drifted apart. Rivers flowed into newly formed seas. Sediments collected along the edges of the continents and on the ocean floor. These layers of sand, mud, and tiny remains of living organisms slowly hardened into sedimentary rocks. Today, these rocks preserve important records of ancient environments, helping scientists understand what conditions were like during different stages of Earth's history. Life continued developing while the continents moved. Although plants and animals had not yet spread across the land, microscopic life in the oceans became increasingly diverse. Different groups of bacteria, algae, and other tiny organisms occupied many marine environments. These living things played an important role in changing the chemistry of the oceans and the atmosphere. They also formed the foundation of early food chains. As hundreds of millions of years passed after Rodinia began breaking apart, the separated continents continued moving across the surface of Earth. Some traveled toward one another, while others drifted farther away. Oceans opened in some places and closed in others. Wherever continents approached each other, the ocean floor between them slowly disappeared beneath one tectonic plate. Eventually, the continents collided once again, producing mountain ranges and creating larger continental masses. The repeated movement of continents eventually led to another ancient supercontinent known as Pangaea. Scientists believe that Pangaea formed around 600 million years ago. It existed for a much shorter time than Columbia or Rodinia, because it remained together for only a relatively brief period before beginning to separate again. Its exact shape is still being studied. Even so, geological evidence suggests that many continental blocks became connected during this stage of Earth's history. The formation of Pangaea once again involved collisions between continents. As ocean basins closed, continental edges met and were compressed together. Thick layers of rock folded under great pressure. Large mountain belts developed where these collisions occurred. Deep within the crust, rocks experienced intense heat and pressure that changed their mineral structure. Today, these altered rocks provide important clues about the ancient collisions. Soon after Pangaea formed, tectonic forces once again began pulling the continents apart. The crust fractured in several regions, allowing new oceans to develop. As before, magma rose into the widening cracks and created fresh ocean crust. The continents slowly drifted away from one another, beginning another stage in the supercontinent cycle. The breakup of Pangea produced several large continental masses that later became important parts of Earth's history. One of these was Gondwana. Gondwana included land that would eventually become present-day Africa, South America, Antarctica, Australia, the Indian subcontinent, and several smaller regions. Gondwana remained together for a very long time and played an important role in later geological events. Other continental blocks existed north of Gondwana. These included Laurentia, Baltica, and Siberia. Laurentia contained much of what later became North America and Greenland. Baltica included areas that later formed parts of northern Europe. Siberia existed as a separate continental block for much of this time. These continents were separated by large oceans that gradually changed shape as tectonic plates continued moving. During this period, the ocean supported increasing diversity of life. Simple organisms continued evolving into more complex forms. Toward the end of this era, the fossil record shows the appearance of larger multicellular organisms. Soft-bodied living things became more common in shallow marine environments. These early organisms represented an important stage in the long history of life. The movement of continents strongly influenced the environments where living things could survive. Shallow seas developed along continental margins, creating habitats rich in nutrients. Rivers carried minerals from the land into the oceans, supporting microscopic life. Changes in sea level sometimes flooded large areas of the continents, creating broad, shallow seas that covered regions now found far above present sea level. The repeated joining and separation of continents also affected volcanic activity. Whenever tectonic plates moved apart, magma rose toward the surface. New volcanic regions formed along rift zones. When plates collided, volcanoes often developed above areas, where one plate descended beneath another. These volcanoes released lava, ash, water vapor, carbon dioxide, sulfur gases, and many other materials into the atmosphere. Volcanic activity contributed to the formation of new rocks and landscapes. Thick layers of lava spread across the surface in some regions. Underground bodies of magma slowly cooled beneath the crust, forming large masses of granite and other igneous rocks. Over time, erosion exposed many of these rocks at the surface, allowing scientists to study events that happened hundreds of millions or even billions of years ago. Mountain building also played a major role throughout every continental cycle. When continents collided, the crust became thicker. Rocks folded into large ridges and valleys. Some rocks were pushed many kilometers upward, while others were forced deep into the crust. Heat and pressure transformed these buried rocks into new forms. After millions of years of erosion removed the upper layers, these deeply buried rocks became exposed at the surface. Erosion constantly changed the appearance of the continents. Wind, rain, rivers, glaciers, and waves slowly wore away mountains. The broken rock was carried into rivers and eventually reached the oceans. There it settled into layers that became sedimentary rocks. These rocks preserve fossils, ripple marks, mud cracks, raindrop impressions, and many other features that allow scientists to reconstruct ancient environments. Each supercontinent left behind evidence that remains visible today. Ancient mountain belts continue across continents that are now separated by oceans. Similar rock formations appear on different sides of the Atlantic Ocean, the Indian Ocean, and other ocean basins. Matching mineral deposits are also found on continents that were once connected. These discoveries strengthen the evidence for repeated supercontinent formation. Modern technology has greatly improved scientists' understanding of these ancient events. Highly accurate methods for measuring the ages of rocks allow researchers to determine when different geological events occurred. Satellite observations measure the present movement of tectonic plates with remarkable precision. Although these measurements cover only a short period of time, they confirm that continents are still moving today, supporting the idea that similar movements shaped Earth's surface throughout its history. Computer models also help scientists study ancient supercontinents. By combining geological evidence, magnetic measurements, fossil discoveries, and information about tectonic plate movement, researchers create detailed reconstructions showing how continents may have been arranged during different periods. These models continue to improve as new discoveries are made in different parts of the world. The supercontinent cycle demonstrates that Earth's geography has never been permanent. Continents have repeatedly assembled into large landmasses and later separated into smaller ones. Columbia, Rodinia, and Pannotia each represented different stages in this long history. Their formation and breakup influenced the arrangement of oceans, the growth of mountain ranges, volcanic activity, climate patterns, sea levels, and the environments where life developed. Every stage prepared the surface of Earth for the next stage, as tectonic plates continued their slow movement across the planet over immense spans of geological time. Long before the world looked the way it does today, Earth's continents were not in their present positions. The land that now forms North America, South America, Africa, Europe, Asia, Antarctica, Australia, Greenland, Madagascar, India, and many other smaller land areas was once scattered across the surface of the planet. These pieces of land moved very slowly over an extremely long period of time. Their movement was so slow that no human could have noticed it during a lifetime, yet over millions of years the changes became enormous. This steady movement eventually brought many separate continents together to form one giant landmass known as Pangea. The formation of Pangea was one of the greatest geological events in Earth's long history, because it changed the shape of the planet's surface, affected the oceans, altered climates, influenced the development of life, and shaped many of the rocks and mountains that still exist today. The story of how Pangea formed began long before the supercontinent itself existed. Earth had already been changing for billions of years. Deep beneath the surface, the planet was still very active. Heat trapped inside Earth caused slow movement within the mantle, which is the thick layer of hot rock beneath the crust. Although this rock remained solid, the very high temperatures and pressure allowed it to move slowly over long periods. These slow movements created large circulating currents inside the mantle. As these currents continued, they pushed and pulled the huge rocky plates that make up Earth's outer shell. Earth's outer layer is broken into many large and small tectonic plates. These plates include both continental crust and oceanic crust. Continental crust is generally thicker and lighter, while oceanic crust is thinner and denser. The plates move only a few centimeters each year, but they never remain completely still. They may move toward one another, away from one another, or slide past each other. Their movement is responsible for earthquakes, volcanoes, mountain building, and the opening and closing of oceans. Before Pangea formed, many continents already existed as separate landmasses. These continents had their own coastlines, rivers, mountains, forests, deserts, and living creatures. Between them lay wide oceans that stretched for thousands of kilometers. Some oceans gradually became smaller as continents slowly drifted toward one another. Other oceans grew larger as different landmasses moved apart. The shape of Earth was constantly changing because plate movement never stopped. One of the most important oceans before the formation of Pangea was the Iapetus Ocean. This ocean separated several ancient continents for a very long time. As tectonic plates continued to move, the ocean floor beneath the Iapetus Ocean slowly sank into the mantle through a process called subduction. During subduction vertifasuran, the heavier oceanic crust bent downward beneath another plate and slowly disappeared into Earth's interior. This process caused the ocean to become narrower over millions of years. As the Iapetus Ocean became smaller, continents that had once been far apart slowly approached each other. The movement was extremely slow, but it continued without stopping. Eventually, the edges of these continents met. When continental crust collided with continental crust, neither side easily sank beneath the other, because both were relatively light. Instead, the crust became compressed, folded, broken, and pushed upward. These powerful forces created long mountain ranges that marked the places where continents had joined together. The formation of mountains during continental collision required an enormous amount of pressure. Thick layers of rock that had once rested beneath shallow seas were squeezed until they folded into huge arches and deep valleys. Some rocks cracked under the stress and moved along large faults. Other rocks were buried deep beneath the surface, where high temperatures and pressure changed their structure. These transformed rocks became metamorphic rocks, providing evidence of the intense forces that acted during the formation of Pangea. As more continents continued moving, additional oceans began to close. Oceanic crust kept sinking into the mantle along subduction zones. Chains of volcanoes often formed above these zones because melting rock from from deep inside Earth rose toward the surface. Over millions of years, these volcanic regions sometimes became attached to nearby continents, adding new land to their edges. Small islands, volcanic arcs, and fragments of crust were gradually joined to larger continents through repeated collisions. The movement of continents did not happen in a straight line. Their paths changed as plate boundaries shifted and mantle currents evolved. Some continents rotated while they moved, others drifted northward, southward, eastward, or westward. These changing directions affected the way different landmasses eventually met. Some collisions occurred almost head-on, while others happened at different angles, producing different patterns of folding and faulting within the rocks. One of the major landmasses involved in the formation of Pangea was Laurentia, which formed the ancient core of present-day North America. Another important continent was Baltica, which included parts of northern Europe. Avalonia was another smaller continent that moved between larger landmasses before eventually joining them. The gradual closing of the Iapetus Ocean allowed these continents to collide. Their collision produced major mountain-building events, whose remains can still be seen today, even though erosion has worn down the mountains over hundreds of millions of years. Farther south, another enormous continent, known as Gondwana, occupied much of the southern hemisphere. Gondwana included what are now South America, Africa, Antarctica, Australia, the Indian subcontinent, Madagascar, and several smaller land areas. For a long time, Gondwana remained separate from the northern continents. A large ocean lay between these landmasses, preventing direct contact. As Earth's plates continued their slow movement, the ocean between Gondwana and the northern continents gradually became smaller. Oceanic crust beneath this ocean entered subduction zones and slowly disappeared into the mantle. This process reduced the distance between the continents year after year, century after century, and million after million years. Eventually, Gondwana approached the northern continents. The collision was not a single event that happened at one moment. Different parts of Gondwana reached the northern landmasses at different times. Some areas collided earlier than others. Each collision created additional mountain ranges, folded rocks, and deep crustal changes. These repeated events slowly united separate continents into one enormous connected landmass. The joining of Africa with parts of Europe played a major role in completing Pangea. As Africa moved northward, the ocean between the two continents narrowed until the continental edges finally met. The impact compressed thick layers of rock and produced extensive mountain building. Rocks were buried deep beneath the surface, heated, squeezed, and later lifted upward as the crust thickened. The geological record preserves many signs of this collision in folded rock layers, metamorphic rocks, and large fault systems. South America also became attached to Africa as the continents assembled. Today their coastlines fit together remarkably well, because they were once connected before later breaking apart again. Their ancient connection is supported by matching rock formations, identical fossil discoveries, and mountain belts that continue from one continent to the other, when the continents are placed back into their earlier positions. North America became connected to Africa and Europe through additional continental collisions. These connections helped complete the northern part of Pangea. Thick mountain belts stretched across areas that are now separated by the Atlantic Ocean. Later, when the Atlantic Ocean opened, these mountain ranges were divided, leaving matching geological features on opposite sides of the ocean. Throughout the formation of Pangea, Earth's crust was constantly changing. Some areas rose to great heights as mountains formed. Other regions sank and became large sedimentary basins, where rivers, lakes, and shallow seas deposited layers of mud, sand, gravel, and the remains of living organisms. Over time, these sediments hardened into sedimentary rocks that preserve valuable information about ancient environments. Rivers flowing across the growing supercontinent carried enormous amounts of sediment from the newly formed mountains. Rain, wind, flowing water, and changing temperatures gradually wore away the mountain slopes through erosion. The broken pieces of rock were transported into nearby basins, where they accumulated layer upon layer over millions of years. These sedimentary deposits became thicker as erosion continued. Earthquakes were common wherever tectonic plates collided. As rocks bent and broke under pressure, energy built up and was suddenly released. These earthquakes sometimes caused large faults to develop within the crust. Although ancient earthquakes cannot be observed directly today, geologists study faulted rocks and other geological evidence to understand the forces that acted during the assembly of Pangea. Volcanic activity also accompanied many stages of continental assembly. Magma generated above subduction zones rose through cracks in the crust and erupted onto the surface. Repeated volcanic eruptions built mountains of lava and ash, while also adding new rock to the growing continents. Some magma cooled beneath the surface instead of erupting, forming large bodies of granite and other igneous rocks deep within the crust. Over time, erosion exposed many of these rocks at the surface. The climate changed as the continents gradually came together. The arrangement of land and sea strongly influenced rainfall, wind patterns, ocean currents, and seasonal temperatures. Coastal regions often received more moisture because of their proximity to the oceans, while areas farther inland became much drier. As Pangea grew larger, some parts of its interior became located very far from the sea, creating broad dry regions where rainfall was limited. The supercontinent was surrounded by a single enormous ocean called Panthalassa. This great body of water covered most of Earth's surface during the late Paleozoic era and much of the Mesozoic era. While Pangea formed one giant, connected landmass, Panthalassa spread around it in every direction. The name Panthalassa comes from ancient Greek words that mean all sea, and this name reflects the fact that it was the world's largest ocean. It was much larger than any ocean that exists today. Nearly every coastline on Earth touched its waters, and almost every marine ecosystem was connected through this vast ocean. The existence of Panthalassa is an important part of Earth's history because the ocean and the land influenced each other in many ways. The movement of water, the transport of heat, the growth of marine life, and the changing climate were all connected to the shape and size of this giant ocean. Scientists study rocks, fossils, and the chemical makeup of ancient sediments to understand what Panthalassa was like and how it affected life on Earth. Since no ocean floor from Panthalassa remains today because it has mostly disappeared through the process of plate tectonics, much of what is known comes from careful study of rocks that once formed along its edges, or from pieces of ancient oceanic crust that were pushed onto continents. Panthalassa covered most of the planet's surface. Pangea occupied a large part of the remaining land area, but the ocean itself stretched across an enormous distance. A person traveling across Panthalassa would have crossed thousands of kilometers of open water without seeing land. Many parts of the ocean were very far from any coastline. These distant waters had their own conditions, with different temperatures, different marine life, and different patterns of movement from the waters closer to land. The shores of Pangea were long and varied. Some coastlines were rocky, while others were made of sandy beaches, muddy flats, river mouths, or shallow lagoons. Rivers carried soil, sand, clay, and minerals from the land into the ocean. These materials settled onto the seafloor where they slowly formed layers of sediment. Over long periods of time, these layers became sedimentary rocks. Today, these rocks provide valuable information about the ancient coastlines and marine environments that once bordered Panthalassa. The ocean did not remain completely calm. Winds blowing across its surface created waves and currents. Storms moved large amounts of water and stirred up sediments near the coast. In deeper parts of the ocean, slower currents carried water across great distances. These movements helped distribute heat, oxygen, nutrients, and tiny living organisms throughout the ocean. Ocean circulation allowed different parts of Panthalassa to remain connected even though the distances were extremely great. The shape of Pangea had a major influence on the way water moved around the planet. Since one huge landmass blocked the flow of ocean currents, water had to travel around the outer edges of the continent. This created very large circulation systems. Warm water moved away from tropical regions toward higher latitudes, while cooler water returned toward lower latitudes. These movements helped control temperatures in different parts of the ocean and influenced weather patterns across the world. The Earth's rotation also affected ocean circulation. As the planet turned, moving water followed curved paths instead of traveling in perfectly straight lines. This created large circular patterns of ocean movement. These circulation systems continued for long periods and helped shape marine climates. They also influenced where nutrients gathered and where different forms of marine life were most successful. The sun provided the energy that drove much of the ocean's circulation. Warm sunlight heated surface waters near the equator. These warm waters became lighter than colder water and spread towards cooler regions. As surface water cooled in higher latitudes, it became denser and slowly sank. This sinking water became part of deeper currents that traveled through the ocean before eventually rising again in other places. These slow but continuous movements formed a global system that transported water over very long distances. The differences in the amount of salt dissolved in seawater also influenced ocean circulation. Water became saltier in areas where evaporation was very strong. In places where large rivers entered the ocean or where rainfall was frequent, seawater became less salty. Differences in temperature and salt content changed the density of seawater. These differences caused water masses to sink or rise, helping create deep ocean circulation. Panthalassa contained many different marine environments. Close to the shore were shallow coastal waters filled with sunlight. These areas supported many forms of life because sunlight reached the seafloor and allowed algae and other simple organisms to grow. These shallow waters became homes for shellfish, corals, sea lilies, sponges, worms, early crustaceans, and many kinds of fish. The rich supply of food attracted larger animals that hunted in these coastal environments. Further from land, the continental shelf gradually gave way to deeper water. Sunlight became weaker with increasing depth. Plants could no longer grow where light failed to reach the sea floor. Animals living in these deeper areas depended on food that drifted down from the surface or on hunting other animals. Many species adapted to these darker conditions and developed bodies suited for life in deeper water. The deepest parts of Panthalassa were cold, dark, and under great pressure. Sunlight never reached these regions. Animals living there depended on organic material, sinking from the waters above, or on chemical processes occurring near the sea floor. Although fossil evidence from these deepest environments is limited, scientists believe that many forms of life lived there, just as deep oceans support many organisms today. The ocean floor itself was constantly changing. new oceanic crust formed at underwater volcanic ridges where molten rock rose from deep inside the Earth. As new crust formed, older ocean floor slowly moved away. Eventually, much of this older crust sank beneath continents or beneath other oceanic plates in areas called subduction zones. Because oceanic crust is recycled in this way, almost none of the original flora of Panthalassa survives today. Volcanic activity beneath the ocean affected marine environments. Underwater volcanoes released heat, minerals and gases into seawater. Lava built underwater mountains and volcanic islands. Some volcanoes eventually rose above sea level, forming islands surrounded by shallow marine habitats. These islands provided new places for marine organisms to live and sometimes became homes for plants and animals after enough soil developed. Earthquakes also affected Panthalassa. Movement along plate boundaries caused sudden shaking beneath the ocean floor. Some earthquakes triggered underwater landslides that carried huge amounts of sediment into deeper water. Others produced large waves that travelled across the ocean. These natural events changed coastlines and affected marine ecosystems. Coral reefs formed in warm, shallow parts of Panthalassa, where conditions allowed reef-building organisms to grow. Ancient reefs were built by different groups of organisms than many modern reefs, although corals were still important members of these communities. Reef systems provided shelter, feeding grounds, and breeding places for many marine animals. Fish, shellfish, sponges, sea stars, and many other organisms found protection among the complex structures created by reef builders. Large areas of the shallow sea floor were covered with soft sediments. Mud, sand, broken shells, and tiny skeletons accumulated over long periods. Burrowing animals dug tunnels through these sediments while feeding or hiding from predators. Their activities mixed the sediments and changed the conditions beneath the sea floor. Many traces of these ancient burrows remain preserved in rocks today. Marine plants and algae formed the base of many food chains. Tiny floating organisms called phytoplankton used sunlight to produce food through photosynthesis. These microscopic organisms multiplied rapidly under favorable conditions and became food for small animals floating in the water. These small animals were eaten by larger fish and other predators. This movement of energy supported the diverse marine ecosystems found throughout Panthalassa. The surface waters of Panthalassa contained enormous numbers of tiny living organisms. Although each individual was very small, together they formed one of the most important parts of the ocean. Their remains settled onto the sea floor after death and gradually formed thick layers of sediment. These sediments became valuable records of ancient ocean conditions because the chemical composition of their tiny shells reflected the temperature and chemistry of seawater. Many different fish lived in Panthalassa. Some had bodies covered with scales, while others possessed protective armor or strong jaws. Sharks were already important predators in many marine environments. Early ray-finned fishes and lobe-finned fishes occupied different ecological roles. Some species fed on tiny floating organisms, while others hunted shellfish or smaller fish. Marine reptiles became important members of ocean ecosystems after the formation of Pangea. Groups such as ichthyosaurs, plesiosaurs, and later mosasaurs appeared during different parts of the Mesozoic era. These animals breathed air but spent most of their lives in the ocean. They hunted fish, squid, and other marine animals. Their fossils provide valuable information about ancient marine food webs and ocean environments. Ammonites became some of the most recognizable animals living in Panthalassa. These relatives of modern squids and octopuses possessed coiled shells divided into many chambers. They lived in a wide range of marine habitats, and evolved into countless species over millions of years. Because ammonites changed rapidly through time, their fossils help scientists determine the ages of rock layers found around the world. Belemnites were another important group of marine animals related to modern squid. Unlike ammonites, they possessed an internal hard structure rather than a large external shell. They swam actively through the water, while hunting smaller animals, and were themselves prey for larger predators. Many shellfish lived on or beneath the sea floor. Clams, brachiopods, gastropods, and other groups filtered food from seawater or grazed on algae. Their shells accumulated after death and often became part of limestone deposits. These fossils reveal much about ancient marine conditions and changes in sea level. Sea lilies attached themselves to the sea floor using long stalks. Their feather-like arms captured tiny food particles drifting through the water. Although they resembled flowering plants, they were actually animals related to sea stars and sea urchins. Many sea lily fossils are preserved in rocks formed beneath shallow ancient seas. Sea urchins, brittle stars, sea cucumbers, and sea stars also lived in many marine environments. These animals fed in different ways depending on their species. Some grazed on algae, some filtered food from seawater, while others hunted smaller animals or scavenged dead material. Sponges formed important parts of many ancient marine communities. They filtered enormous amounts of water while removing tiny food particles. Their activities helped maintain water quality and provided shelter for smaller organisms living among their structures. The amount of oxygen dissolved in seawater varied from place to place. Surface waters usually contained more oxygen because they were mixed by waves and exposed to the atmosphere. Deeper waters sometimes contained much less oxygen, especially where circulation was weak. Low oxygen conditions affected which animals could survive in different parts of the ocean. Climate strongly influenced Panthalassa. During warmer periods, tropical waters expanded, while colder waters occupied smaller regions. Changes in global temperature affected sea level, ocean circulation, and marine ecosystems. Even relatively small shifts in climate sometimes caused important changes in the distribution of marine species. Rainfall patterns over Pangea also influenced the ocean. Rivers flowing from wet regions carried large amounts of freshwater, nutrients, and sediments into coastal waters. These inputs supported the growth of marine organisms, but also changed water chemistry near river mouths. Dry regions contributed much less freshwater, leading to saltier coastal waters. Strong seasonal winds affected parts of Panthalassa. These winds influenced surface currents and sometimes caused nutrient-rich deep water to rise toward the surface. When this occurred, microscopic plant life often increased because additional nutrients became available. Larger marine animals benefited as food became more abundant. Sea level changed many times while Panthalassa existed. During periods of higher sea level, shallow seas spread across low-lying parts of continents. These inland seas connected with the larger ocean and created additional marine habitats. During periods of lower sea level, coastlines moved outward, exposing large areas of land that had previously been underwater. One important body of water connected with Panthalassa was the Tethys Ocean. This broad tropical sea lay between different parts of Pangea and supported rich marine ecosystems. Warm waters flowing through the Tethys influenced ocean circulation and allowed many marine species to spread between different regions. The coastlines of Pangea changed slowly over millions of years as plate tectonics continued. Mountains rose where continents collided, valleys formed where the crust stretched apart, rivers changed course, New coastlines developed while older ones disappeared. Each change affected nearby marine environments by altering sediment supply, water depth, and shoreline shape. Sediments deposited along continental margins recorded these changes in great detail. Layers of sandstone indicated ancient beaches and shallow coastal environments. Mudstones formed in quieter waters. Limestone developed where shells and other calcium-rich remains accumulated. Together, these rocks provide a detailed record of ancient seas surrounding Pangea. Marine fossils found within these rocks help scientists reconstruct ancient environments. Different species preferred different depths, temperatures, and water conditions. By studying fossil communities, researchers can estimate whether an area was once a shallow lagoon, an open continental shelf, a coral reef, or a deeper marine basin. Tiny chemical differences preserved within fossil shells also provide valuable information. The proportions of certain forms of oxygen and carbon preserved in shells reflect the temperature and chemistry of ancient seawater when the organisms were alive. These measurements allow scientists to estimate past ocean temperatures and understand long-term climate changes. Ocean circulation influenced weather across Pangea. Warm currents carried heat away from tropical regions, while cooler currents transported colder water toward lower latitudes. These movements affected evaporation, rainfall, cloud formation, and wind patterns. Areas close to warm currents often experience different climates than regions influenced by colder water. The enormous size of Pangea meant that storms could travel across very long distances. Strong winds generated large waves that shaped coastlines through erosion and sediment transport. Beaches shifted, sandbars formed, and river mouths changed over time as waves and tides constantly reworked coastal sediments. Tides also influenced coastal environments. The gravitational pull of the moon and the sun caused regular rises and falls in sea level. These tidal movements flooded mudflats, salt marshes, and shallow coastal areas before exposing them again. Many marine organisms adapted to these changing conditions. Life within Pangea continued to evolve throughout the existence of Pangea. New species appeared while others disappeared through natural extinction. Environmental changes, volcanic activity, climate shifts, and changes in sea level all influenced which organisms survived. Marine ecosystems remained active and constantly changing over millions of years. Toward the later history of Pangea, the supercontinent began to break apart as tectonic forces stretched and fractured the continental crust. New ocean basins slowly opened between separating landmasses. As these young oceans expanded, Pangea gradually lost some of its dominance. Ocean circulation patterns changed as new waterways developed between the separating continents. The opening of new oceans altered marine habitats. Coastal environments formed along newly created shorelines. New shallow seas developed where continental crust sank below sea level. Marine organisms spread into these expanding habitats, leading to the appearance of new ecological communities. Although Pangea eventually disappeared as Earth's continents continued moving into their modern positions, its influence remained recorded in rocks across every continent. Ancient marine sediments, fossils, volcanic rocks, and chemical signatures preserve evidence of the world's greatest ocean and the many environments that existed within it. These records continue to help scientists understand Earth's changing surface, the history of marine life, the movement of tectonic plates, and the long history of the oceans that have covered most of the planet. The interior of Pangea was one of the most unusual places that has ever existed on Earth. Pangea was a single enormous landmass that brought together almost all of the continents into one connected body of land. Because it stretched across such a vast part of the planet, many areas were located very far from any coastline. Some places in the center of this giant continent were thousands of kilometers from the nearest ocean. This great distance from the sea had a strong effect on the climate, the land, the rivers, the plants, the animals, and every living thing that made its home there. Scientists have spent many years studying rocks, fossils, minerals, ancient soils, and other evidence to understand what these inland regions were like. Their discoveries show that life in the center of Pangea faced many challenges that were different from those found closer to the coasts. The oceans play an important part in controlling the climate of Earth. Water heats up and cools down more slowly than land. Because of this, places near the sea often have temperatures that stay within a smaller range throughout the year. The sea also provides moisture that forms clouds and brings rain to nearby land. In the center of Pangea, this helpful influence from the oceans became much weaker. Air that carried moisture from the sea often lost most of its water long before reaching the middle of the continent. By the time the air arrived in these distant regions, it had become much drier. This meant that rainfall was often limited, and many parts of the inland areas remained dry for long periods. The climate in these central regions changed with the passing seasons. During the hottest months, the ground absorbed large amounts of heat from the sun. Since there was no nearby ocean to reduce the heating, temperatures could rise to very high levels during the daytime. The land became hot, and the air above it also warmed quickly. At night, the opposite happened. The land lost heat rapidly after sunset, because there was no large body of water nearby to keep temperatures steady. Nights could become much cooler than the daytime. This large difference between day and night affected every living thing that lived in these regions. The yearly cycle also brought changes in temperature. During warmer seasons, long periods of heat placed great pressure on plants and animals. During cooler seasons, temperatures dropped more than they did near the coasts. The lack of nearby oceans allowed the land to heat and cool very quickly. Organisms living in these regions had to survive these changing conditions year after year. Rain did not fall evenly across the interior of Pangea. Some years may have brought enough rain to fill rivers and lakes. Other years may have been much drier. Long dry seasons were common in many places. During these dry periods, streams became smaller, ponds dried up, and many rivers carried less water than usual. Plants that depended on regular rainfall struggled to survive. Only those that could live with limited water remained healthy throughout the dry months. The soil reflected these changing weather conditions. In wet periods, water soaked into the ground and supported the growth of plants. During long dry periods, the soil hardened and cracked. Wind lifted loose dust into the air and carried it across the landscape. Layers of dust settled over wide areas. Some of these layers later became part of the rock record that scientists study today. These ancient rocks help researchers understand how dry many parts of the interior once were. Many of the rivers flowing across the center of Pangea behave differently from rivers in wetter climates. Some rivers flowed throughout the entire year because they were supplied by rainfall from distant mountain regions. Other rivers only carried water after heavy rains. During dry months, they became empty channels with exposed gravel, sand, and mud. When sudden storms finally arrived, large amounts of water rushed through these channels. Fast-moving floods carried rocks, branches, mud, and sand across the land before the rivers slowly returned to lower levels. Flooding played an important role in shaping the landscape. Heavy rain falling over a short time could quickly fill dry river channels. Water spread across low areas and left behind layers of mud and fine sand. When the floodwaters disappeared, These fresh layers became places where new plants could grow if enough moisture remained. Floods also buried the remains of plants and animals, helping preserve fossils that scientists have discovered many millions of years later. Lakes formed in many parts of the interior, but not all of them lasted for long periods. Some lakes remained full for many years because rivers continuously supplied fresh water. Others expanded during wet seasons and shrank during dry seasons. In especially dry years, some lakes disappeared almost completely. As the water evaporated, minerals dissolved in the lake water remained behind. Thick deposits of salt and other minerals slowly accumulated. These mineral layers provide important clues about the changing climate of ancient Pangea. Many low-lying basins collected water after rainfall. These temporary wetlands became important places for life. Plants quickly spread across moist ground. Small animals gathered around the remaining pools. Larger animals visited these areas to drink. As the dry season returned, many of these wetlands slowly disappeared. Organisms either moved away, entered resting stages, or died if they could not find another source of water. The winds blowing across the interior often became strong because the land stretched over such great distances without interruption by large bodies of water. Dry soil and loose sand could easily be lifted into the air. Dust storms sometimes spread across wide regions. Fine particles remained suspended in the atmosphere before settling back onto the land. These storms affected visibility, covered plants with dust, and changed the surface of the ground. Sand dunes developed in many dry areas. Wind pushed loose grains of sand into long ridges and hills. These dunes slowly shifted as winds changed direction. The movement of sand buried older surfaces while uncovering others. Ancient sandstone formations found today still preserve the patterns left by these moving dunes. These rocks provide clear evidence that deserts covered large areas of the interior. Not every part of central Pangea was completely dry. Some regions received more rainfall because of local geography. Mountain ranges affected the movement of moist air. Valleys collected water, flowing downhill. Rivers supported narrow strips of greener land, even where the surrounding countryside remained dry. These areas became important habitats for plants and animals that needed reliable water supplies. Mountain ranges influenced local climates in several ways. Air moving toward mountains rose upward. As it climbed, it cooled and released some of its moisture as rain on one side of the mountains. The opposite side often became much drier because much of the moisture had already fallen. This created regions with different amounts of rainfall even within the interior of Pangea. The plants growing far from the coast had to cope with difficult conditions. Many species developed ways to reduce water loss. Some had thick outer coverings on their leaves. Others had leaves that were narrow or small. These features reduced the amount of water escaping into the air. Some plants grew deep root systems that reached underground moisture hidden beneath the dry surface. Others spread wide roots close to the surface so they could quickly absorb rainwater after storms. Certain plants stored water inside their tissues during wet periods. This stored water helped them survive later when rain became scarce. Other species completed much of their growth during the wetter part of the year. They produced seeds before the dry season became severe. The seeds remained inactive until favorable conditions returned. Large forests did not cover every inland region. Dense forests usually needed greater amounts of rainfall than much of the interior received. Instead, many areas contained open woodlands, scattered trees, hardy shrubs, seed ferns, conifers, and other plants able to survive with limited moisture. These plants formed the foundation of the inland ecosystems by providing food and shelter for many animals. Conifers became especially successful in many dry regions because they possessed features that reduced water loss. Their leaves often remained on the plant throughout the year, allowing continuous growth whenever conditions improved. Their seeds could survive changing weather and spread across wide areas. Different species occupied different environments depending on local rainfall and soil conditions. Seed ferns also played an important role in many inland ecosystems. Although they resembled true ferns in appearance, they reproduced through seeds instead of spores. This allowed them to reproduce successfully even when standing water was limited. Seeds offered greater protection for young plants during dry conditions. The grasses that dominate many modern landscapes had not yet evolved during much of Pangea's history. Instead, other plant groups filled similar roles within the ecosystems. Low-growing plants covered patches of ground where enough moisture remained. Mosses and other simple plants occupied damp places near streams and lakes. Plant growth changed from year to year depending on rainfall. Wet years produced more leaves, branches and seeds. Dry years reduced plant growth. Some plants died, leaving open ground where only the hardiest species survived. These changing conditions affected every animal that depended on plants for food. Plant remains accumulated on the ground after leaves and branches fell. Tiny organisms broke down this material and returned nutrients to the soil. However, decomposition often slowed during very dry periods, because many decomposers needed moisture to remain active. When rainfall returned, these organisms became more active again. The insects living in the interior occupied many different habitats. Some fed directly on plants, others hunted smaller insects. Many laid eggs in moist soil or near water. The changing seasons strongly affected insect populations. After rainfall, food became more abundant and insect numbers often increased. During extended dry periods, many insects became less active or entered resting stages until better conditions returned. Spiders, scorpions, and other small hunters also lived throughout these inland regions. They helped control insect populations and formed part of complex food chains. Many sheltered beneath rocks, inside cracks, or among plant roots where temperatures remained slightly lower and moisture lasted longer. Amphibians depended heavily on water because many laid eggs that required moist conditions to develop. In the drier parts of central Pangea, amphibians remained close to rivers, lakes, ponds, and wetlands. During prolonged droughts, their available habitat became much smaller. Some species buried themselves in mud to survive until rain returned. Reptiles became especially successful across much of the inland landscape because they were less dependent on water than amphibians. Their skin reduced water loss, and their eggs possessed protective coverings that allowed reproduction away from permanent water. These features gave reptiles an important advantage in dry environments. Many reptile species occupied different ecological roles. Some fed mainly on plants, others hunted insects, fish, amphibians, or other reptiles. Large predators searched for prey across open ground, while smaller reptiles hid among rocks, fallen branches, or vegetation. Each species became adapted to particular habitats within the inland environment. Early relatives of dinosaurs appeared during the later stages of Pangea. Some of these animals explored inland environments where they found food and shelter. Over time, dinosaurs became increasingly successful in many regions of the supercontinent. Different groups adapted to different climates and landscapes, including dry inland plains. Plant-eating reptiles often traveled between feeding areas as seasonal conditions changed. When local plants became scarce, these animals moved toward regions with better vegetation. Their movements influenced predator populations because meat-eating animals followed the plant eaters in search of food. Predators living in the interior needed large hunting areas because prey was often spread across wide distances. Scarce water also brought animals together around rivers and lakes. These gathering places became important hunting grounds where predators waited for opportunities to catch weakened or distracted prey. Waterholes became centers of activity throughout many dry regions. Animals arrived to drink, feed on nearby vegetation, or hunt other animals. The ground around these water sources often became worn from repeated use. Footprints left in soft mud sometimes hardened before being buried by new sediment. These preserved tracks provide valuable evidence about ancient animal behavior. Competition for water increased during dry seasons. Different species often depended on the same rivers, ponds, or lakes. Animals visited these places at different times of day. Some came during cooler morning hours, while others appeared later. This reduced direct contact between certain species and allowed more animals to use limited water supplies. Many animals adjusted their daily activities to avoid extreme daytime heat. Some remained active mainly during early morning or evening when temperatures were lower. Others rested in shaded places during the hottest part of the day before becoming active again after sunset. Burrows beneath the ground provided cooler temperatures and protection from dry air. Burrowing became an important survival strategy for many small animals. Underground tunnels remained cooler and often retained more moisture than the surface. Eggs, young animals, and stored food could all be protected within these shelters. Burrows also provided safety from predators. The changing climate influenced reproduction. Many animals timed the birth of their young or the laying of eggs to coincide with seasons when food and water were more available. This increased the chances that offspring would survive during their earliest stages of life. Disease and parasites also affected inland ecosystems. Dry conditions sometimes limited the spread of organisms that required standing water. Wet seasons allowed many parasites to reproduce more successfully. Animals weakened by drought often became more vulnerable to disease because of poor nutrition and limited water. Fires occasionally swept across parts of the inland landscape when dry vegetation ignited after lightning strikes. Once started, flames spread through dry plants and fallen branches. Fires removed old vegetation but also returned nutrients to the soil. After rainfall, new plants often grew in burned areas, providing fresh food for grazing animals. The atmosphere above central Pangea also reflected the changing climate. Hot air rising from the heated land created powerful weather systems. Storms sometimes developed quickly after long periods of dry weather. These storms brought strong winds, heavy rain, thunder, and lightning. Although the rain provided much-needed water, sudden downpours also caused flooding and erosion. Erosion constantly reshaped the inland landscape. Wind carried away loose soil, while rivers cut into the ground during floods. Hills slowly wore down over very long periods. Sediments traveled downstream and settled in valleys, lakes, and inland basins. These accumulated layers later hardened into rock, preserving a record of ancient environments. Minerals within the soil changed according to climate. Dry conditions encouraged the buildup of salts near the surface as water evaporated. In wetter periods, rainfall washed some minerals deeper into the ground. Different soil layers formed over time, each recording past environmental conditions. Scientists study ancient soils known as paleosols to understand these environments. The color, texture, mineral content, and structure of these soils reveal information about rainfall, temperature, drainage, and plant growth. Red-coloured soils often indicate that oxygen was present during soil formation under warm conditions. Other colours may show different chemical processes linked to changing climates. The rocks of central Pangea preserve evidence of repeated environmental change. Thick sandstone layers indicate ancient deserts with shifting dunes. Mudstones point toward rivers, lakes, or floodplains. Coal deposits usually represent wetter environments, where abundant plant material accumulated faster than it decomposed. Alternating rock layers reveal that many inland regions experience cycles between wetter and drier conditions. Fossils found within these rocks provide direct evidence of ancient life. Leaves preserve details about plant shapes and growth patterns. Fossil wood reveals yearly growth influenced by seasonal climate. Animal bones, footprints, nests, eggs and burrows help scientists reconstruct ancient ecosystems. Even fossilized pollen grains provide valuable information because different plant species produce distinctive pollen. Pollen traveled through the air and settled into lakes, rivers, and wetlands. Layer after layer accumulated over many thousands of years. Scientists examine these preserved grains under microscopes to identify ancient plants and estimate how vegetation changed through time. Climate changes did not occur everywhere at exactly the same rate. Different parts of the interior experienced local variations depending on mountains, elevation, nearby rivers, and shifting weather patterns. Some regions gradually became wetter, while others became drier. Ecosystems continuously adjusted to these changing conditions. As the continents slowly moved because of plate tectonics, the position of different inland regions also changed. Areas once located deep within the continent gradually moved closer to coastlines as Pangea later began breaking apart. New oceans formed between separating landmasses. Places that had experienced dry continental climates eventually came under greater influence from nearby seas. Before this breakup, however, the enormous size of Pangea remained the main reason why its interior differed so greatly from coastal environments. Moist air simply could not carry enough water across such vast distances to provide steady rainfall everywhere. This produced extensive dry regions, unlike those found on smaller continents surrounded by nearby oceans. Animals living in these inland habitats displayed remarkable flexibility. They responded to seasonal changes by migrating, changing feeding habits, using shelters, adjusting activity times, storing energy, or reproducing during favorable periods. Species unable to adapt often disappeared from particular regions, while better adapted species expanded into newly available habitats. Food chains within these ecosystems depended on the limited plant growth supported by available rainfall. Plants converted sunlight into food. Plant-eating animals fed on leaves, stems, seeds, and other plant parts. Predators hunted herbivores and smaller hunters. Tiny organisms broke down dead material and returned nutrients to the soil. Every part of this system depended directly or indirectly on water availability. Even small changes in rainfall affected the entire ecosystem. Increased rain encouraged plant growth, which supported larger populations of herbivores. More herbivores provided additional food for predators. During droughts, the opposite occurred. Reduced plant growth lowered food supplies, herbivore numbers declined, and predators also faced greater difficulty finding enough prey. Seasonal migration became an important part of survival for some species. Animals traveled along river valleys or across open plains in search of fresh vegetation and reliable water. These movements may have covered long distances, depending on local geography and yearly climate conditions. young animals faced especially difficult challenges. They required steady food supplies while still learning to survive. Parents that protected nests, eggs, or young often selected locations close to dependable water and shelter. Successful breeding depended heavily on favorable environmental conditions. Many reptiles laid eggs in warm soil where natural heat helped development. The choice of nesting location affected survival because flooding, drought, predators, and temperature all influenced whether young animals successfully emerged. The inland environment also affected body size. Large animals required large amounts of food and water. They often needed extensive home ranges that included multiple feeding and watering sites. Smaller animals could survive on fewer resources and sometimes occupied specialized habitats unavailable to larger species. Different elevations within the interior created additional environmental diversity. Higher ground often experienced cooler temperatures than nearby lowlands. Valleys trapped water and supported richer plant growth. Rocky hillsides provided shelter for animals adapted to rugged terrain. Each landscape supported its own community of living organisms. Chemical weathering of rocks proceeded more slowly in very dry regions because water is required for many reactions that break down minerals. Physical weathering became more important. Daily heating and cooling caused rocks to expand and contract repeatedly. Over long periods, this weakened the rocks, causing cracks to form. Wind carrying sand also gradually wore away exposed rock surfaces. Groundwater remained an important hidden resource beneath the surface. Rainwater that soaked into the ground slowly moved through layers of rock and sediment. Springs occasionally brought this underground water back to the surface, creating valuable habitats where plants and animals gathered even during dry seasons. Many inland rivers changed course over time. Floods cut new channels while abandoned channels filled with sediment. These shifting rivers created broad floodplains where fresh soil supported plant growth after each major flood. Volcanic activity affected some regions of Pangea during different periods of its history. Volcanic eruptions released ash that settled across the landscape. Ash added minerals to the soil after weathering. Large eruptions also influenced climate by releasing gases and tiny particles into the atmosphere. These events sometimes caused temporary environmental changes that affected ecosystems across wide areas. The interaction between climate, geology, water, plants, animals, and microorganisms shaped every part of the inland world. No single factor acted alone. Changes in rainfall influenced rivers. Rivers affected soils. Soils supported plants. Plants fed animals. Animals spread seeds, disturbed soil, and became food for predators. Microorganisms recycled nutrients that allowed new plant growth. Every part remained connected through natural processes. The interior of Pangea therefore represented an enormous collection of landscapes shaped by limited ocean influence, changing rainfall, strong seasonal temperature differences, powerful winds, shifting rivers, dry plains, scattered woodlands, temporary wetlands, deserts, rocky uplands, and fertile valleys. Across these environments, life continued to adapt to conditions created by living far from the coastlines, where distance from the surrounding oceans shaped ecosystems through the steady influence of climate, water availability, soil development, plant growth, animal behavior, and the continuous changes occurring across the vast center of the ancient supercontinent. The climate of Pangea was one of the most important parts of the history of this ancient supercontinent. It affected the land, the oceans, the atmosphere, the rivers, the forests, the deserts, and every living thing that existed during that time. Scientists have spent many years studying rocks, fossils, ancient soils, mineral deposits, and other forms of evidence to understand what the weather and climate were like while Pangea existed. These studies have shown that the climate across the giant landmass was very different from place to place. Some regions received large amounts of rain throughout the year, while others remained dry for very long periods. Some places experienced very high temperatures during the daytime, while other places had cooler conditions because of their location or elevation. The size of Pangea played a major role in creating these different environments because the enormous landmass changed the way air moved around the planet and affected how moisture travelled from the oceans into the interior. Pangea existed during the late Paleozoic era and much of the Mesozoic era. During this long period, Earth's climate changed many times. These changes happened because of movements of the continents, changes in the atmosphere, volcanic activity, shifts in sea levels, and changes in the amount of carbon dioxide and other gases in the air. The arrangement of the continents also changed the paths of ocean currents, and these currents influenced temperatures around the world. Since almost all of Earth's major landmasses were joined together into one giant continent, the climate behaved differently from the climate of the modern world. The outer edges of Pangea were close to the great ocean called Panthalassa. The areas near the coast usually received more moisture because winds blowing from the ocean carried water vapor onto the land. Clouds formed more easily in these regions, leading to rainfall that supported rivers, lakes, forests, and many different kinds of plants. Coastal areas often had conditions that were more suitable for life because fresh water was more available. Many animals and plants lived in these regions, leaving behind fossils that helped scientists understand the environments of the time. The center of Pangea was very different. Because the land stretched for thousands of kilometers away from the nearest ocean, moist air could not easily reach the interior. As winds moved inland, much of their moisture had already fallen as rain near the coasts. By the time these air masses reached the middle of the continent, they were much drier. This created large dry regions where rainfall was limited. Many of these inland areas became deserts or semi-dry environments, with only small amounts of plant life. Rivers were less common, and water sources could disappear during long dry seasons. Many parts of central Pangea experienced very hot summers because sunlight heated the large land surface. Land warms more quickly than water, so the huge continent absorbed heat rapidly during the daytime and throughout the warm seasons. During the night, the land also lost heat more quickly than the nearby oceans. This created large differences between daytime and nighttime temperatures. Some places became very hot during the day and much cooler after sunset. These daily changes affected plants and animals that had to survive under these conditions. Seasonal changes were also strong across much of Pangea. During warmer months, temperatures increased across many inland regions. During cooler months, temperatures dropped as sunlight became less direct in different parts of the world. Because the continent was so large, these seasonal changes could become very noticeable far from the moderating influence of the oceans. Living organisms needed to adapt to these yearly cycles in order to survive. Scientists have discovered evidence of ancient deserts across many regions that once formed the center of Pangea. Sandstone layers preserve the shapes of ancient sand dunes that were created by strong winds moving across dry landscapes. These rocks contain patterns that show the direction of the wind as it pushed loose sand into large dunes. The size and arrangement of these dunes tell scientists that dry conditions lasted for long periods. Wind continued shaping the land whenever rain was scarce and vegetation remained limited. Ancient desert rocks also contain minerals that form when water evaporates. These minerals include salts and other substances left behind after shallow lakes or inland seas dried up. Such deposits provide important evidence that evaporation was often greater than rainfall in many regions. Water collected during wetter periods but disappeared again as hot conditions returned. Rainfall patterns across Pangea varied greatly depending on location. Coastal regions often received regular rain because of moist air coming from the surrounding oceans. Inland areas generally received much less precipitation. Mountains also influenced rainfall. When moist air reached mountain ranges, it rose into the atmosphere and cooled. As the air cooled, water vapor condensed into clouds, leading to rain or snow on one side of the mountains. After crossing the mountains, the air became drier, creating regions with much less rainfall beyond the mountain slopes. Large river systems developed wherever rainfall remained high enough to support flowing water. These rivers carried sediments across the land and deposited mud, sand and gravel into lakes, floodplains and coastal areas. Over time, these sediments hardened into sedimentary rocks. Scientists study these rock layers today to learn about ancient rainfall, river flow, flooding, and seasonal weather changes. Some rivers flowed continuously throughout the year because they were supplied by regular rainfall. Other rivers only carried water during wet seasons and became nearly dry during long periods without rain. The changing flow of these rivers left different patterns in the rocks, allowing geologists to recognize seasonal climates that existed millions of years ago. The atmosphere during the time of Pangea was also different from today's atmosphere. The amount of carbon dioxide in the air changed throughout this long period. At certain times, higher levels of carbon dioxide contributed to warmer global temperatures. Volcanic eruptions released carbon dioxide into the atmosphere, adding to natural climate changes. Over long periods, weathering of rocks and the growth of plants helped remove some carbon dioxide from the atmosphere, influencing global temperatures once again. Plants played an important role in the climate. Large forests absorbed carbon dioxide during photosynthesis and released oxygen into the atmosphere. Forests also affected local temperatures by providing shade and releasing moisture into the air through their leaves. Areas with thick vegetation usually had higher humidity than nearby dry regions. Plant cover also reduced soil erosion because roots held the ground together during rainfall. Different kinds of forests grew across various parts of Pangea depending on local climate conditions. Wet regions supported dense forests with many species of ancient trees, seed ferns, horsetails, and other plants. Swamp forests developed in low areas where water remained for long periods. These wetlands supported many animals, insects, amphibians, and early reptiles. Dry regions supported plants that were able to survive with less water. Some developed thick outer coverings that reduced water loss. Others produced seeds that remained protected until enough moisture became available for growth. These adaptations allowed plants to survive long dry seasons that would have prevented less specialized species from living there. Animals also adapted to changing climates across Pangea. Species living in deserts often became active during cooler parts of the day. Some remained inside burrows to avoid the hottest temperatures. Others developed body features that helped reduce water loss or improved their ability to travel across dry ground. Animals living in wetter forests had access to more food and water, supporting greater biological diversity. The position of Pangea across different latitudes also influenced climate. Areas closer to the equator generally received stronger sunlight throughout the year, leading to warmer temperatures. Regions farther from the equator experienced cooler conditions because sunlight reached the surface at lower angles. The southern parts of Pangea extended toward polar regions during parts of its history, allowing glaciers and ice sheets to develop during colder periods. Evidence for ancient glaciers has been found in rocks from southern parts of the supercontinent. These rocks contain scratches made as glaciers moved slowly across the land. Large stones carried by ice were dropped into softer sediments as glaciers melted. Such evidence shows that some regions experienced cold climates even while other parts of Pangea remained warm and dry. The transition from colder climates to warmer climates happened over millions of years as Earth's atmosphere changed and the continents slowly shifted into new positions. Ice gradually disappeared from many southern regions, allowing forests and other vegetation to expand into areas that had once been covered by glaciers. Ocean circulation also affected the climate of Pangea. The giant Panthalassa Ocean surrounded most of the continent, while the Tethys Ocean lay between different parts of the landmass. Ocean currents transported heat from one region to another. Warm currents raised temperatures along certain coastlines, while cooler currents lowered temperatures in other areas. These moving waters also influenced rainfall because evaporation from warm ocean surfaces supplied moisture to the atmosphere. Changes in ocean circulation sometimes altered weather patterns across large parts of the world. If currents shifted, regions that once received regular rainfall could become drier. Other regions could begin receiving greater amounts of precipitation as moist air followed different paths. These long-term changes influenced plant communities, animal populations, and the development of ecosystems. Storms formed over the oceans and sometimes moved inland. Coastal regions likely experienced heavy rain during powerful storms, especially where warm ocean waters supplied large amounts of moisture. Strong winds could damage forests, reshape coastlines, and transport large amounts of sediment into rivers and lakes. Flooding sometimes covered broad floodplains with layers of mud that later became sedimentary rock. Lightning from storms may have started natural fires in forests during dry seasons. Evidence from charcoal preserved in ancient rocks suggests that wildfires occurred in some parts of Pangea. These fires cleared vegetation from certain areas, allowing new plants to grow after rains returned. Fire became one of the natural processes affecting ecosystems in regions where dry and wet seasons alternated. Some parts of Pangea experienced monsoon-like weather systems because of the enormous size of the continent. During warmer seasons, the land heated more rapidly than the surrounding oceans. Warm air rose over the continent, drawing moist air inland from nearby seas. This process produced seasonal rainfall across certain regions. During cooler seasons, the direction of air movement changed, bringing drier conditions. These yearly cycles influenced river flow, plant growth, and animal behavior. Ancient soils provide valuable information about climate. Different types of soil form under different environmental conditions. Some ancient soils indicate long periods of rainfall, while others formed in dry deserts, where evaporation exceeded precipitation. The color, mineral content, and structure of these soils help scientists reconstruct the ancient environments of Pangea. Fossils of plants also reveal climate conditions. Leaves, wood, pollen, and spores preserved in rocks show which plant species lived in different areas. Since each plant has certain environmental requirements, scientists can estimate rainfall, temperature, and humidity based on fossil discoveries. Dense forests indicate wetter climates, while sparse vegetation suggests drier conditions. The growth rings inside fossil wood provide another source of information. Some fossil trees contain clear annual growth rings that formed because of seasonal changes. Wide rings usually indicate years with favorable growing conditions, while narrow rings suggest periods of limited water or cooler temperatures. These patterns allow scientists to study ancient climate changes over many years preserved within a single fossil tree. Temperature differences across Pangea were affected not only by latitude but also by elevation. Mountain regions remained cooler than nearby lowlands because air temperatures decrease with height above sea level. Snow could remain on high peaks even when surrounding valleys stayed much warmer. Streams flowing from these mountains supplied fresh water to lower regions, supporting forests and wildlife. The Permian period was the last period of the Paleozoic era. It began about 299 million years ago and ended about 252 million years ago. During this long stretch of time, Earth looked very different from the planet that exists today. Almost all of the world's land had come together to form one enormous supercontinent called Pangea. This giant landmass stretched across a huge part of the planet and was surrounded by a single vast ocean known as Panthalassa. Smaller seas also existed in some places, especially along parts of the coastline, but the greatest part of the world's land was connected into one continuous continent. The formation of Pangea changed almost every part of Earth's environment. It affected the movement of air, the flow of ocean water, the amount of rainfall, the spread of deserts, and the places where plants and animals could survive. The joining of many continents into one large landmass created new mountain ranges, changed rivers, and altered coastlines. These changes shaped life on Earth throughout the Permian period. During the early part of the Permian, Pangea had already been formed through the slow movement of tectonic plates over many millions of years. Continents that had once been separated by wide oceans had slowly moved toward each other. Their collisions lifted mountains, folded rocks, and closed ancient oceans. These events continued to shape the land throughout the Permian as the Earth's crust remained active. The center of Pangea was very far from the oceans. Since large bodies of water help control temperature and bring moisture into the air, the interior of the supercontinent became much drier than coastal regions. Rain clouds often lost much of their moisture before reaching the middle of the continent. As a result, many inland areas received very little rainfall. Large deserts covered wide regions of central Pangea. Dry winds carried sand across open landscapes. Sand dunes formed and shifted over long periods. Some of these ancient dunes later hardened into sandstone, which can still be found today. These rocks help scientists understand the dry climate that existed during much of the Permian. Temperatures across Pangea varied greatly depending on location and season. Coastal areas often had milder conditions because nearby oceans reduced sudden changes in temperature. Inland regions experienced hotter summers and colder winters because they lacked the influence of large bodies of water. Days could become extremely hot under clear skies, while nights sometimes became much cooler. The southern parts of Pangea had experienced widespread glaciation before the Permian began. Large ice sheets covered parts of what are now South America, Africa, Antarctica, India, and Australia when these lands were joined together. As the Permian continued, the climate gradually became warmer, causing many of these glaciers to melt. The melting ice raised sea levels in some regions and supplied water to rivers and lakes. As glaciers disappeared, new environments developed. Plants spread into areas that had once been covered by ice. Rivers carried sediment across the land, creating fertile floodplains where many forms of life became established. Forests expanded into suitable regions, although dry conditions prevented forests from growing everywhere. The atmosphere during the Permian differed somewhat from today's atmosphere. Oxygen levels changed over time and were generally lower than during some earlier periods of the Paleozoic era. Carbon dioxide levels also varied as volcanic activity, plant growth and natural chemical processes continued to influence the composition of the atmosphere. These changes affected climate and the living conditions for plants and animals. The oceans surrounding Pangea covered most of Earth's surface. Panthalassa was the largest ocean that had ever existed. Its waters stretched across enormous distances. Ocean currents moved heat around the planet, helping shape weather patterns and marine environments. Smaller seas along the edges of Pangea provided important habitats for many marine organisms. Life in the oceans remained rich and varied throughout much of the Permian. Coral reefs supported many different animals. Sponges, sea lilies, shellfish, brachiopods, bryozoans, and many other invertebrates lived together in shallow marine waters. Fish continued to diversify, filling different ecological roles in rivers, lakes, coastal waters, and deeper parts of the sea. Sharks were among the important predators in Permian oceans. Different kinds of sharks occupied different environments. Some hunted near the sea floor, while others searched for prey in open water. Their sharp teeth and well-developed senses made them successful hunters. Many bony fish also thrived during the Permian. Some fed on tiny floating organisms. Others hunted smaller fish or crushed hard-shelled animals with powerful jaws. Rivers and freshwater lakes supported their own unique communities of fish, amphibians, and other aquatic life. Ammonoids became especially successful during the Permian. These animals lived inside coiled shells and moved through the water using jet propulsion. They occupied many marine habitats and developed into numerous different species. Their fossils are very useful for scientists because different species appeared and disappeared over relatively short periods of geological time. Plants on land continued to evolve throughout the Permian. Earlier swamp forests that had dominated parts of the Carboniferous period gradually declined in many regions as climates became drier. Plants that required constant wet conditions became less common in areas where rainfall decreased. Seed plants became increasingly important. Unlike many earlier plants that depended heavily on water for reproduction, seed plants were better suited to dry environments. Seeds protected young plants during development and allowed them to survive difficult conditions until they could begin growing. Conifers spread widely across many parts of Pangea. These trees were well adapted to dry climates. Their leaves reduced water loss, allowing them to survive where other plants struggled. Conifer forests covered many upland and inland regions. Other groups of seed plants also flourished. Ginkgo relatives, seed ferns, cycads, and several extinct plant groups formed forests and woodlands across different climates. Each type occupied environments where its characteristics provided advantages. Ferns continued growing in moist areas along rivers, lakes, and wetlands. Mosses and other small plants covered damp ground in suitable habitats. Plant communities varied depending on rainfall, temperature, soil conditions, and elevation. The spread of different plants influenced many other forms of life. Leaves, seeds, roots, and wood provided food for plant-eating animals. Forests created shelter and nesting places. Fallen plant material enriched soils and supported fungi, insects, and many small organisms. Insects continued to diversify during the Permian. Beetles appeared and became increasingly successful. Dragonflies, cockroaches, grasshopper relatives, and many other insects occupied forests, deserts and wetlands. Some insects fed on leaves, others on wood, pollen, spores or dead organic material. The evolution of insects also influenced plant reproduction. Although many flowering plants had not yet evolved, insects still interacted with plants in many different ways. They spread spores, fed on plant tissues, and served as food for larger animals. Life on land experienced important changes during the Permian because reptiles became increasingly diverse. Earlier amphibians had dominated many environments, especially those with abundant water. Reptiles gradually expanded into drier regions because their bodies were better adapted for life away from permanent water sources. One major advantage of reptiles was the amniotic egg. This type of egg contained protective membranes that allowed embryos to develop on land without depending directly on ponds or lakes. This adaptation opened many new environments for reptiles and contributed greatly to their success. Among the most important land animals of the Permian were synapsids. These animals are often called mammal-like reptiles, although they were not true reptiles in the modern scientific sense. Synapsids eventually gave rise to mammals many millions of years later. Early synapsids included sail-backed animals such as Dimetrodon. Although often mistaken for dinosaurs, Dimetrodon lived long before the first dinosaurs appeared. It possessed strong jaws, filled with sharp teeth, and hunted many kinds of prey. The tall sail along its back was supported by long spines extending from the backbone. Scientists continue studying its exact purpose, with ideas including temperature regulation, display, or species recognition. Edaphosaurus was another sail-backed synapsid, but unlike Dimetrodon, it mainly fed on plants. Its teeth and digestive system allowed it to process tough vegetation. Large body size helped it reach different plant sources, while providing protection from some predators. As the Permian continued, more advanced synapsids called therapsids appeared and gradually became widespread. Therapsids displayed many characteristics that later became important in mammals. Their legs were positioned more directly beneath the body, allowing more efficient movement than the sprawling posture of many earlier animals. Some therapsids were plant-eaters, others hunted smaller animals. Different species occupied many ecological roles across Pangea. Their teeth often became more specialized, with different shapes serving different purposes, such as cutting, tearing, or grinding food. Dicynodonts became one of the most successful groups of plant-eating therapsids. Many had beak-like mouths with only a pair of tusks, or sometimes no tusks at all. Their jaws were effective at processing vegetation, allowing them to feed on many different plants. Gorgonopsians were among the largest predators of the late Permian. They possessed long canine teeth and strong jaws suited for hunting large prey. These animals occupied the highest levels of many land food chains across parts of Pangea. Amphibians continued living successfully in rivers, lakes, swamps, and wetlands. Many large amphibians hunted fish and smaller animals in freshwater environments. Their dependence on water limited where they could live, especially in the driest regions of central Pangea. Freshwater ecosystems supported many different organisms. Rivers flowed from mountain ranges toward inland basins or coastal regions. Seasonal flooding deposited fresh sediment across floodplains, supporting plant growth and providing habitats for aquatic animals. Lakes varied greatly in size and depth. Some remained filled throughout the year, while others expanded and shrank with changing rainfall. These freshwater bodies became centers of life within otherwise dry landscapes. Mountain ranges formed during earlier continental collisions influenced climate and ecosystems. High elevations received more rainfall than nearby lowlands. Streams flowing down mountain slopes supplied water to valleys below. Different plants and animals occupied these cooler environments. Volcanic activity continued in some regions during the Permian. Volcanoes released lava, ash, gases, and minerals that reshaped local landscapes. Fresh volcanic rock gradually weathered into fertile soil, where plants later became established. Earth's crust remained active beneath Pangea. Although the supercontinent appeared stable, tectonic forces continued operating deep below the surface. Stress slowly accumulated within the crust, preparing the way for changes that would eventually break Pangea apart millions of years later. Many rock layers formed during the Permian preserve evidence of ancient rivers, deserts, forests, lakes, and shallow seas. Sedimentary rocks contain fossils that allow scientists to reconstruct ancient environments. Fossil pollen, leaves, footprints, bones, shells, and burrows each provide valuable information about life during this period. Climate shifted several times during the Permian. Some regions became drier, while others experienced increased rainfall. Sea levels rose and fell as glaciers melted. Tectonic activity changed ocean basins, and other geological processes altered the volume of seawater held within oceans. Chemical processes in oceans also changed throughout the Permian. The amount of oxygen dissolved in seawater varied in different places. Nutrients entered the oceans through rivers and volcanic activity. Marine organisms responded to these changing conditions as ecosystems continued evolving. Near the end of the Permian, Earth experienced one of the greatest biological crises in its history. This event is known as the End Permian mass extinction. It marked the boundary between the Permian period and the Triassic period. The extinction affected both land and marine ecosystems on a worldwide scale. Scientists continue studying the exact sequence of events that caused this extinction. The strongest evidence points to enormous volcanic eruptions in a region that is now part of Siberia. These eruptions continued for an extremely long time and released vast amounts of lava across the landscape. The volcanic eruptions also released huge quantities of carbon dioxide, sulfur dioxide, methane, and other gases into the atmosphere. These gases changed Earth's climate and affected both land and sea environments. Global temperatures increased significantly, creating difficult conditions for many living organisms. Warmer temperatures caused additional environmental changes. Oceans absorbed much of the extra carbon dioxide, making seawater more acidic. Acidic water made it harder for many shell-forming organisms to build and maintain their shells and skeletons. Ocean circulation also changed. In some places, deep waters received much less oxygen. Large regions of the oceans became oxygen poor, making survival difficult for many marine animals. Organisms that depended on oxygen-rich water disappeared from affected areas. Some scientists also believe that oxygen-free conditions allowed certain bacteria to produce poisonous hydrogen sulfide gas. This gas may have entered both the oceans and the atmosphere, creating further stress for living organisms. Ash from volcanic eruptions spread across large areas. Particles in the atmosphere temporarily affected sunlight reaching Earth's surface. Rainfall patterns shifted as atmospheric conditions changed. These combined effects placed increasing pressure on ecosystems already struggling with rising temperatures. Plant communities suffered greatly during the extinction. Many forests disappeared as climate conditions became too harsh. Soil erosion increased after vegetation declined. Rivers carried greater amounts of sediment into lakes and oceans, changing aquatic habitats. As plants disappeared, animals that depended on them for food also declined. Plant-eating species struggled to find enough vegetation. Predators lost their prey. food chains became unstable across many environments. Marine ecosystems experienced especially severe losses. Coral reefs almost completely disappeared. Many brachiopods, trilobites, crinoids, ammonoids, and countless other marine organisms suffered enormous population declines or vanished completely. Entire ecological communities collapsed. Trilobites, which had existed for hundreds of millions of years, became completely extinct during the end Permian event. They had survived many earlier environmental changes, but did not survive this final crisis. Many groups of insects also experienced heavy losses. Although insects as a whole survived, numerous ancient lineages disappeared forever. Land animals faced equally serious challenges. Many therapsids, amphibians, reptiles, and other vertebrates became extinct. Only a limited number of species survived to reproduce in the changing world that followed. Scientists estimate that around 9 out of every 10 marine species disappeared during this extinction. On land, about 7 out of every 10 vertebrate species became extinct. These losses permanently changed Earth's biodiversity. Recovery from the extinction required millions of years. Surviving species slowly spread into habitats left empty by extinct organisms. New ecosystems gradually developed as evolution produced new forms of life suited to the changing environment. The end Permian mass extinction created conditions that later allowed new groups of reptiles to expand during the Triassic period. Among these were the distant ancestors of dinosaurs, crocodilians, pterosaurs, and many other reptiles that would later become important parts of Earth's ecosystems. The extinction also influenced the evolutionary history of synapsids. Although many groups disappeared, a few survived. These survivors eventually gave rise to the first true mammals during the Mesozoic era. The world after the end Permian extinction differed greatly from the world that had existed before it. Forests, rivers, deserts, mountains, coastlines, and oceans remained, but the living communities within them had changed dramatically. Many familiar Permian species were gone, while the survivors began establishing new populations across Pangea as life slowly adapted to the environmental conditions that followed the greatest mass extinction in Earth's history.